Hello everyone, very good evening to all of you. Good evening everyone, good evening. So am I audible and visible? Please type in a chat box. Am I audible and visible? Good evening, good evening, good evening. Okay, so shall we start today's session? Shall we start today's session? So in previous session, we discussed about the concept of continuum, right? In the previous section, in the last session, we discussed about the concept of continuum, and after that we discuss about some fundamental fluid properties like mass density, weight density, and the specific volume, right? So let's start today's session. In today's session we will discuss about the fundamental properties like specific gravity, right, relative density, viscosity, right? So let's start this session. Okay, so density or mass density is already covered. So what is the density or mass density? It is a measure of inertia or heaviness, right? Density or mass density is nothing but the measure of inertia or heaviness, and it is a ratio of mass per unit volume. It is ratio of mass per unit volume, and density is denoted by rho. Density is denoted by rho. So we can say rho is equal to mass per unit volume, right? And what is the unit? What is the SI unit? That SI unit is kg per meter cube, right? That SI unit is kg per meter cube. Now next fundamental fluid property is weight density or specific weight. Weight density or specific weight is denoted by gamma. So that weight density or specific weight, that is equal to weight per unit, right? Weight per unit volume, right? It is the ratio of weight to volume, and weight is denoted by mg and volume is denoted by v. So we can write that weight density is, this is nothing but the rho into g. And what is the SI unit of weight density, right? What is the SI unit of weight density? So that is nothing but the Newton per meter cube, right? Newton per meter cube. Now come to the next fundamental property, that is a specific volume. Specific volume, and specific volume is denoted by a small v, and this is nothing but the total volume per unit mass. Total volume per unit mass, right? So specific volume, that is v by m, or you can say this is reciprocal of the density, that is reciprocal of the density. So you can define a specific volume in another way also, that specific volume is nothing but the reciprocal of the mass density, right? And if you are comparing the specific volume of liquid and the gases, if you are comparing the specific volume of liquid and gases, so we can easily compare. We know that, right? We know that in general the density of liquid is higher than the density of gas, right? Density of liquid is higher than the density of gas. So if I'm talking about the specific volume, So specific volume of liquid is lesser than the specific volume of gas, right? So from the knowledge of density, we can easily compare the specific volume of liquid and the gas. Okay, now come to the next fundamental property, that is a specific gravity, right? Specific gravity. Next fundamental property is specific gravity. So any idea about the specific gravity? Anyone having idea about the specific gravity? Any idea about specific gravity? Specific gravity is denoted by S. Specific gravity is denoted by S. And specific gravity, it is a ratio of density of, right? Specific gravity is defined as the ratio of density of one fluid to density of the standard fluid, right? Density of a fluid, density of an unknown fluid, I can say it is defined as density of unknown fluid to density of standard fluid, right? So we can write in this way that density of unknown fluid to density of standard fluid, right? Now I am multiplying with G in numerator and the denominator, so we can write in this way also. This is the weight density of unknown fluid to weight density of standard fluid, right? Now what is the standard fluid? What is the standard fluid? What is the standard fluid? What is a standard fluid? What is a standard fluid? Right? What is a standard fluid? So in case of liquid, what is the standard fluid? And in case of the gases, what is the standard fluid? So in case of the liquid, or and even in solids also, not only in liquids, in solids also, that standard fluid is water. That standard fluid is water. Right? And we know that what is the density of water? We know that what is the density of water? That is 1000 kg per meter cube. Right? Now in case of the gas, what is the standard fluid? So in case of the gas, air is standard fluid. In case of the gas, air is standard fluid. And what is the density of air at STP? What is the density of air at STP? That is 1.205 kg per meter cube, right? This is at standard temperature and pressure at STP. So in case of liquid and the solid, that standard fluid is water, whereas in case of the gases, right, in case of the liquids and the solids, standard fluid is water, whereas in case of the gases, that standard fluid is air. Okay, now see here, let us consider benzene. Right? Let us consider benzene. Benzene having a specific gravity of 0.88. Let us consider benzene. Benzene having a specific gravity, that is 0.88. So can you tell me what is the density of the benzene? Can you tell me what is the density of the benzene. What is the density of the benzene? You can calculate easily, na? Right? You can easily calculate the density of benzene. Right? So specific gravity of the benzene is, specific gravity of benzene is 0.88, and this is equal to density of benzene, to this density of standard fluid, and that is water. So from here we can easily calculate the density of benzene. We can easily calculate the density of benzene, and that is equal to 880 kg per meter cube. Okay, what is the unit of the specific gravity? What is the unit of specific gravity? What is unit of specific gravity? What is the unit of specific gravity? What is unit of specific gravity? So specific gravity is unitless. Specific gravity is unitless. Right? Specific gravity is unitless. Right? No unit. So specific gravity, right? Specific gravity does not have any unit. Specific gravity is unitless. Okay. Now see here. Now see here. Now, if I am talking about the liquids, right? If I am talking about the liquids, right? So can you tell me the instrument or device by using that we can measure the specific gravity of a liquid? Can you tell me what is the device by which we can measure the specific gravity of liquid? Can you tell me? Very good, beta, very good. Right? Important note point. Specific gravity of liquid. Specific gravity of liquid is measured by very good, that is hydrometer. Right? Specific gravity of liquid is measured by the hydrometer. Right? Can you tell me about the hygrometer? Right? Most of the student confuse between the hydrometer and the hygrometer. Right? Most of the student confuse between the hydrometer and the hygrometer. So beta, hydrometer is a device which is used to measure the specific gravity of a liquid. Can you tell me about hygrometer? What is a hygrometer? By using the hygrometer, which property is measured? By using hygrometer, which property is measured? Can you tell me? So humidity, specific humidity, or simply I can say humidity. Right? Specific humidity or simply humidity is measured by hygrometers. Right? Specific humidity or humidity is measured by the hygrometer. So don't confuse between the hydrometer and the hygrometer. Hydrometer is used to measure the specific gravity of liquid, whereas hygrometer is used to measure the specific humidity or moisture content present in the air. Right? Hygrometer is used to measure the humidity or moisture content present in the air. Okay, now come to the next property, which is a relative density. Come to the next property, which is a relative density. Now, what is a relative density? 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 Relative density. But a relative density is you can say relative density is a ratio of density of one fluid with respect to reference fluid. Right? Density of one fluid with respect to reference fluid. So if you are comparing the density of one fluid with respect to some reference fluid, then that is a relative density, right? So see here, let us consider there are two fluids, fluid number A and the fluid number B. Fluid number 1, your fluid number A having density that is rho 1, and the fluid number B having density that is rho 2. Now I am comparing the density of fluid A with respect to density of fluid B. Right? That fluid B is not a standard fluid. Fluid B is not a standard fluid. So what I am doing here, I am comparing the density of fluid number A with respect to density of fluid number B. So in this case, we can write relative density that is equal to rho 1 by rho 2. I am comparing the density of fluid number A with respect to density of fluid number B. Is it clear? Is it clear? So beta, this is the relative density. This is the relative density. Now see, can I write specific gravity is, can I write, very very important point, specific gravity is relative density. Specific gravity is relative density, but relative density need not be specific gravity, need not be specific gravity. Can I say? Tell me guys, can I say? Specific gravity is relative density, but relative density need not be a specific gravity. Is it true or false? Is it true or false? Specific gravity is relative density. Yes, specific gravity is relative density, but relative density need not be a specific gravity. Right? If this reference fluid, if this reference fluid is a standard fluid, then relative density is a specific gravity. Is it clear to everyone? Is it clear to everyone? Specific gravity is the relative density, but relative density need not be specific gravity. So I hope you can understand this line. I hope you can understand this line. Right? If this rho 2 is the density of the standard fluid, then relative density becomes specific gravity, na? Right? So yes, we can say specific gravity is a relative density, but relative density need not be a specific gravity. It may be. Next, very very important point. See, what happened in some time, right? Sometime in problem, the relative density is given, right? Sometime in problem, relative density is given. Specific gravity is not mentioned in problem. Relative density is mentioned. But the reference fluid is not mentioned in the problem. See here, if in a problem relative density of a fluid is given, but reference fluid is not mentioned, in that case standard fluid is considered as a reference fluid. That means relative density is considered as a specific gravity. So let us consider in a problem, relative density is given. Let us consider that is 2. Let us consider relative density is given. Let us consider that is 2. Right? For any object or for any body, that relative density that is equal to 2. So what is the density of that body? What is the density of that body? What is the density of that body? In problem, relative density is mentioned, that is 2. Now I'm asking what is the density, right? So in this case, see that standard, so in this case, the reference fluid is not mentioned, na? Reference fluid is not mentioned. So by default, that standard fluid is taken as a reference fluid, right? By default, that standard fluid is taken as a reference fluid, right? So in this case, we can easily find out the density. So this is 2 multiplied by 1000 kg per meter cube. So this is equal to 2000 kg per meter cube. Is it clear to everyone? Right. So this is a very, very important point. This is very, very important point. If relative density is given in the problem, but the reference fluid is not mentioned, then standard fluid is considered as a reference fluid. And what is the standard fluid? We already discussed. What is the standard fluid? In case of the liquid and solid, that standard fluid is water, whereas in case of the gases, that standard fluid is air, right? So we can say in this case, whenever the relative density is mentioned in the problem and the reference fluid is not given, then no need to worry, that relative density is nothing but the specific gravity only, right? So sometime you are facing such type of problem, so don't confuse, na? Okay, now come to the next fluid property, very, very, very important fluid property, that is the viscosity. Come to the next fluid property that is very, very important, that is a viscosity. Viscosity. We already discussed little bit about the viscosity in Newton's law of viscosity. We already discussed little bit about the Newton's law of viscosity, right? Now come to the basic definition of the viscosity. What is the viscosity? What is the viscosity? So viscosity is a measure to, right? Viscosity is measure to resistance, measure of resistance to shear deformation rate or the resistance to flow, right? What is the viscosity? Viscosity is measure of resistance to shear deformation rate or resistance to flow. Now see, because of the viscosity, that fluid layers, right, fluid layers experiences the frictional force, or you can say shear force, when the fluid layers are trying to move each other. And if I'm talking about the viscosity, viscosity is a fluid property which comes when fluid when fluid is in motion. Though viscosity is a fluid property, but it come into picture when fluid is in motion, right? Next very, very important point, in case of the ideal fluid. So if you classify the fluid in a very basic level, right? If you classify the fluid in a very basic level, then there are 2 types of fluid, right? One is the ideal fluid and second one is the real fluid. One is the ideal fluid and second one is the real fluid. If you classify the fluid, basic classification, forget about the Newtonian, non-Newtonian, right? That is a different level classification. But if I'm talking about the basic level classification, so fluid is categorized as ideal fluid and the real fluid. Ideal fluid and the real fluid, right? So in case of the ideal fluid, if I'm talking about the ideal fluid, so ideal fluid has 0 viscosity, or we can say no viscosity. Ideal fluid does not have any viscosity, or we can say ideal fluid have 0 viscosity, right? And what is the reason of viscosity in any fluid? What is the reason of viscosity, right? In any fluid, that viscosity is because of cohesive force, between the fluid molecules, and the second important factor is the molecular momentum exchange, right? And what is the cohesive force? What is the cohesive force? The cohesive force is nothing but the intermolecular attraction force between the same molecules, right? There are two types of intermolecular forces now. One is a cohesive force and second one is a adhesive force. Here we are talking about the cohesive force. Cohesive force is nothing but the intermolecular attraction force between the same molecules. That is a cohesive force, right? So if I am talking about the reason of viscosity, so there are two reasons. That first reason is the cohesive force between the fluid molecules, and the second reason is the molecular momentum exchange, right? So if I am talking about the viscosity, see here, what is the viscosity? The first important thing, what is the viscosity? Viscosity is nothing but the resistance to flow. In a simple language, viscosity is nothing but the resistance to flow, right? And viscosity come into picture when fluid is in motion, right? Viscosity come into picture when fluid is in motion. Though viscosity is a fluid property, but viscosity come into picture when fluid is in motion. Getting my point? And in case of the ideal fluid, if I am talking about the ideal fluid, in case of the ideal fluid, that viscosity is zero, right? Or we can say, for the ideal fluid, there is no viscosity, right? It is inviscid. No viscosity, that means inviscid, right? And if you are asking about the reasons, right, reasons of viscosity, so there are two factors which are responsible for the fluid viscosity. The first factor is a cohesive force. Cohesive force is nothing but the intermolecular attraction force between the same molecules, and the second one is the molecular momentum exchange. Okay, now come to the, if you want to learn more thing about the viscosity, so to understand the viscosity, what I am doing here, I am considering a plate. Let us consider plate number 1. Plate number 1, right? And let us consider this is the bottom plate, and this plate is stationary, right? This is the stationary plate. This is the stationary plate, right? Now above the stationary plate, let us consider there is a fluid, and above this fluid there is another plate. Let us consider there is another plate which is a top plate. There is another plate which is a top plate. So this is the top plate. This is the top plate, right? Now I am applying the shear force in this top plate, right? That is a F. And because of this shear force, what is the velocity of the top plate? Let us consider the velocity of the top plate. Let us consider that is V, right? Now let's draw coordinate system. So this is the x-axis and this is the y-axis. This is the x-axis, this is the x-axis, and this is the y-axis. Okay, so if I ask you at y is equal to 0, at y is equal to 0, what is the fluid layer velocity? What is the fluid layer velocity? So let us consider u is the local fluid layer velocity. Local fluid layer velocity. And what is the up? That up is the plate velocity? What is the UP? That UP is the plate velocity. Plate velocity. So if I ask you at y is equal to 0, what is the velocity of the fluid layer at y is equal to 0? What is the velocity of the fluid layer? I am talking about this fluid layer. So at y is equal to 0, fluid layer having same velocity which is equal to the plate velocity, right? And at y is equal to 0, plate is stationary, so we can say at y is equal to 0 that u is equal to 0. Now in a similar fashion, at y is equal to delta, let us consider here to here, this gap is delta, right? This gap is delta. So at y is equal to delta, that u is equal to, again, that is equal to up, and this is equal to v. And these conditions are called the no slip condition. These conditions are called no slip condition. I already discussed about the no slip condition, why it is called no slip condition. Local fluid layer velocity means, see, if I am talking about the fluid, so this fluid consists number of layer na. If you see the fluid layer consists, this fluid consists number of layer na. So if I am talking about the velocity here, right, what is the velocity of this layer? If I am talking about the velocity of this layer, so velocity is not same na. Each layer don't have the same velocity, right? Layer which is present at y is equal to 0 having 0 velocity, whereas layer which is present at y is equal to delta having velocity that is equal to v. So each layer having different velocity, right? That's why I am using the term here local. Local means, right, here the velocity varies in a y direction, right? In this case velocity varies in a y direction. That's why I am using the word local, right? Local means this u is a function of y. This u is function of y. Is it clear? Yes. Okay. So this is the no slip condition. Why it is called no slip condition, beta? Why it is called no slip condition? Why it is called no slip condition? Why it is called no slip condition? I already discussed now. When fluid is in contact, with solid surface. When fluid is in contact with solid surface, then there is no relative velocity. Between plate and, or then there is no relative velocity between solid surface and fluid layer. That means whatever the velocity of the plate have, same velocity is for fluid also, right? When fluid is in contact with the solid surface, then there is no relative velocity between solid surface and the fluid layer. Hence, therefore no slipping occurs. occurs. Right, slipping occurs, slipping between the solid surface and the fluid occurs, right? Slipping between solid surface and the fluid occurs when there is a relative velocity. If there is when there is no relative velocity, when there is no relative velocity, there is no slipping, right? That's why this condition is known as the no slip condition. That's why this condition is known as the no slip condition. Is it okay? Now, if I ask you which fluid property is responsible for the no slip condition, which fluid property is responsible for the no slip condition? Which fluid property is responsible? Which fluid property is responsible for the no slip condition? Obviously, that is a viscosity. That is a viscosity. Viscosity is a fluid property. Viscosity is a fluid property. Viscosity is a fluid property responsible for no slip condition. No slip condition. Right? Viscosity is a fluid property which is responsible for the no slip condition. Yes, very good. Right? Viscosity is nothing but the resistance to flow. Viscosity is nothing but the resistance to flow. So if I am talking about this layer, if I am talking about this layer, if I am talking about the layer which is present at y is equal to 0, the layer which is present at y is equal to 0, why this layer having the same velocity? Why this layer having the same velocity as the plate? Because of the viscosity, obviously. Getting my point? So viscosity is a fluid property which is responsible for the no slip condition. So if I ask you, in case of the ideal fluid, the no slip condition is applicable or not? In case of the ideal fluid, no slip condition is applicable or not? In case of the ideal fluid, no slip condition is applicable or not? If I am talking about the, see, let us consider, again I am considering plate. So let us consider this is the plate. Let us consider this is the plate. This is the plate, right? And see here, above this plate there is a ideal fluid which is flowing, right? This is the ideal fluid, right? This is the x direction and this is the y direction. So can we write at y is equal to 0? Can we write at, in case of the ideal fluid, when the ideal fluid is flowing over the plate, so can we say at y is equal to 0, u is equal to 0? Can we say in this case at y is equal to 0, that u is 0? Can we say? Can we say? No. We can't say, because in case of the ideal fluid, that viscosity is 0. In case of the ideal fluid, there is no viscosity. So if there is no viscosity, there is no slip. There is no slip condition. Are you getting my point? So in case of the ideal fluid, if this fluid is ideal, so at y is equal to 0, u is not equal to 0. U is not equal to 0. I hope you can understand this. Okay, so this is the bottom plate, and let us consider, I am considering a top plate here. Let us consider. And this top plate, again same thing, I am applying a shear force on this top plate. And because of that shear force, the top plate is moving with velocity v. Right? So in this case, when the fluid is ideal, this condition is not applicable. Right? So in case of the ideal fluid, see, this is the, I will show you the velocity distribution. Each layer having the same velocity. This is the velocity variation or velocity distribution in case of the ideal fluid. Right? Because in case of the ideal fluid, none of the layer experiences the shear resistance. There is no shear resistance because this is the ideal fluid. There is no viscosity. So in this case, each layer having the same velocity. Is it clear? Is it clear or not? So in case of ideal fluid, or I can write here, in case of ideal fluid, no slip condition is not applicable. No slip condition is not applicable. No slip condition is not applicable. Each layer having the same velocity because the fluid layer does not experiences any resistance or any shear resistance. Is it clear to everyone? Is it clear or not? Is it clear or not? Now come to our analysis. So in our case, there is a fluid is a real, right? Now see, if I'm talking about this particular section, I'm talking about this particular section, and if I ask you what is the velocity of fluid layer at y is equal to 0, that is 0, right? And what is the velocity of fluid layer at y is equal to delta, so that is equal to v, so the layer present at y is equal to delta, fluid layer present at y is equal to delta having velocity that is equal to v, and the layer present at y is equal to 0 having velocity that is equal to 0, right? So beta, this velocity here, velocity is 0, and here the velocity, let us consider that is 10 meter per second, right? Here at this point at y is equal to 0, that velocity is 0, and at y is equal to delta, let us consider some numerical value. Let us consider that is 10 meter per second. So what about the layer which is present in between the bottom layer and the top layer, right? Obviously, if this layer having velocity 0 and this layer having velocity 10 meter per second, so as we are moving in the y direction, the velocity increases. As we are moving in the y direction, that velocity increases. So let us consider this velocity is 0. Let us consider this velocity is 0.5 meter per second. This is the 1 meter per second. Then let us consider this is a 1.5 meter per second. This layer having velocity 1.5 meter per second. This layer having velocity 2 meter per second. This layer having velocity, let us consider 5 meter per second, and so on. So in this way it is clearly, we can see in the y direction, there is in a y direction, that velocity changes with respect to y. See here. So it is very much clear in a y direction, there is a velocity variation with respect to y. So we can say, see here the velocity is function of y. As we are moving in the y direction, the velocity changes in y direction. At y is equal to 0, the fluid layer having 0 velocity, and y is equal to delta, fluid layer having velocity v, or we can say 10 meter per second. So it is very much clear, as we are moving in the y direction, that velocity changes. Now if I am talking about the two layers, let us consider any two layer. Let us consider this layer, right? Let us consider layer number 1 and layer number 2. Now if you consider these two layers, right, now in between the layer number 1 and layer number 2, the relative velocity exists or not, right? in between layer number 1 and layer number 2 relative velocity exists or not? Better forget about the what is the velocity profile. This velocity profile may be linear, maybe parabolic, maybe second degree parabola, maybe third degree parabola, maybe anything. Forget about that velocity profile. Here I am only saying that velocity is a function of y. What kind of function? I don't know. That we will see later on. No? Okay, so if I am considering two layer number 1 and layer number 2, so in between layer number 1 and layer number 2, the relative velocity exists. Yes. And beta, whenever the relative velocity exists, then friction come into picture na. Then friction come into picture na. If I am talking about block number A and the block number B. Block number A and the block number B. Block number A is moving with 5 meter per second velocity, and block number B also moving with 5 meter per second velocity. If I ask you what is the friction between the interface? What is the friction between the interface of block number A and the block number B? Can anyone tell me what is the friction? Right. If I ask you on a very simple question, let us consider two block number A and block number B. Block number A is moving with 5 meter per second and block number B is moving with 5 meter per second. And if I ask you what is the friction between, or what is the friction at the interface? What is the friction? But there is no friction, na? There is no friction, na? In this case, that friction is zero, na? In this case, friction is zero, na? In this case, friction is zero. Why zero? Why zero? Why zero? Because no relative velocity. Because no relative velocity between block A and block B. Block A and block B. So friction come into picture, right? Friction come into picture when the relative velocity is present. Friction come into picture when relative velocity is present. So let us consider, right? This is the case number 1. Now come to the case number 2. Right? Block number B and this is the block number A. Now block number A is moving with 5 meter per second and block number B is moving, let us consider 10 meter per second. In this case, definitely friction is present. In this case, definitely friction is present. In this case, friction is not zero. Friction is present. In this case, friction is present. Right? Now, this is the same case now. Whatever we discussed here, see, if we consider two layer in the ideal fluid, let us consider this is the layer number 1 and this is the layer number 2. And if I ask you what is the friction force, here? So there is no friction force. Right? This layer does not experiences any friction force because there is no relative velocity. If relative velocity is present, then friction come into picture. Right? Now here, in this particular case, if I consider layer number 1 and layer number 2, friction force is present. Friction force is coming into picture because layer number 1 and layer number 2 having different velocity. In between layer number 1 and layer number 2, relative velocity exists. I hope you can understand this. Okay. Now see here. So if I draw the free body diagram of the layer number 2, see here. Layer number 2. So if you see from the top view, this is the fluid layer, na? This is the fluid layer. Just 1 minute, na? Fluid layer is with pink color. So this is the top view of fluid layer. Right? This is the top view of fluid layer. This is the top view of the fluid layer. Okay, now See here, friction force is acting like this. Friction force is acting like this. This is the friction force. This is the friction force. And let us consider this layer having area that is capital A. These layer having area that is capital A. Right? This is the friction force. And this friction force is parallel to the plane now. This friction force is parallel to the plane now, parallel to the plane. So this friction force is parallel to the plane, so we can say this friction force having a shear nature. That's why it is also called shear force. That is also called shear force. So you can say friction force, or you can say shear force, or you can say resistance force also. Resistance force also. Right? You can say friction force, same thing now, friction force. You can say friction force. You can say shear force. You can say resistance force, same thing, resistance force. And why this friction force come into picture? Why this friction force come into picture? Because of the viscosity, layer having different velocity, because of the viscosity, layer having different velocity. Since layer having different velocity, that's why friction come into picture. Right? And this layer experiences the friction force. Let us consider that is Ff. And this friction force is parallel to the plane, right? Parallel to the plane of a layer. That's why this friction force also you can say this is a shear force, or you can say resistance force. So beta, if this friction force is parallel to area A, so definitely this friction force is a shear force, or this friction force having a nature of shear. So definitely the shear stress come into picture. So if I ask you what is the shear stress experienced by this layer, what is the shear stress experienced by this layer? What is the shear stress experienced by this layer? Shear stress experienced by fluid layer. Shear stress experienced by the fluid layer. So what is the shear stress that is experienced by the fluid layer? That is equal to tau. The shear stress is present by the tau. So we can say this tau is equal to shear force per unit area. Right? This is the shear stress experienced by the fluid layer. And that shear stress simply we can say shear force per unit area. Right? And everyone knows what is the unit of the shear stress? What is the unit of shear stress? Newton per meter square, or simply we can say Pascal. Newton per meter square, or simply we can say Pascal. Now, come to the Newton's law of viscosity. Come to the Newton's law of viscosity. Come to the Newton's law of viscosity. Remember Newton's law of viscosity? Remember Newton's law of viscosity. I already discussed little bit about the Newton's law of viscosity. Newton's law of viscosity. What is the Newton's law of viscosity? 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 Tell me. What is the Newton's law of viscosity? So as per Newton's law of viscosity, as per Newton's law of viscosity, this shear stress experienced by the fluid layer. Shear stress experienced by the fluid layer. Shear stress is directly proportional to shear stress is directly proportional to shear stress is directly proportional to shear strain rate or angular deformation rate or angular deformation or angular deformation rate, right? The shear stress is directly proportional to angular deformation rate, right? So we can say that tau is directly proportional to d phi by dt. Tau is directly proportional to d phi by dt, right? What is the d phi by dt? The d phi by dt is nothing but the angular deformation. We already discussed, right? When we discuss about the difference between the solid and the fluid. So I already discussed about this d phi by dt. The d phi by dt is nothing but the rate of angular deformation. So the shear stress experienced by the fluid layer is directly proportional to d phi by dt. Now if you remove the proportionality sign, then proportionality constant come into picture now. Then proportionality constant come into picture, and this proportionality constant, right, this is the proportionality constant, and this proportionality constant is very, very important. Why it is important? Because this proportionality constant is a fluid property, right? This proportionality constant is fluid property. This proportionality constant is fluid properties, which shows the resistance against the flow. And this fluid property is known as the viscosity or absolute viscosity, or dynamic viscosity, or coefficient of viscosity, and it is denoted by Greek letter, which is mu. So we can say tau is equal to, that is mu d phi by dt, right? Tau is equal to mu d phi by dt, right? Now let us consider this is the equation number 1. Okay, now see here, just 1 minute na, I again draw the plate. So this is the plate na, this is the plate, this is the bottom plate, and this is the top plate, right? Bottom plate is stationary, whereas top plate is moving with certain velocity, with constant velocity, that is v, right? And in between there is a fluid, right? And if I am talking about this particular section, so at this particular section, see here the velocity is 0, here the velocity, that is v, and this is the velocity variation, right? U is a function of y, okay? Now see, this is the coordinate system, this is the x-axis and this is the y-axis. Now at a distance y from the plate, from the bottom plate, at a distance y from the bottom plate, I am considering this layer. I am considering this layer, and at a distance y plus dy, at a distance y plus dy. So let us consider this is dy. I am considering another layer. So let us consider this layer, right? So at a distance y, from the bottom plate, at a distance y from the bottom plate, I am considering this layer and this layer. Let us consider this is the layer number 1 and this is the layer number 2, right? So at a distance y from the bottom plate, I am considering these two layers. The first layer is at a distance y and the second layer is at a distance y plus dy. Okay, now see here, if you zoom these two layers, right? If you zoom these two layers, so this is the layer number 2 and let us consider this is the layer number 1, right? This is the layer number, this is layer number 1 and this is the layer number 2. The distance between layer number 1 and layer number 2, distance between layer number 1 and layer number 2, that is dy. Distance between layer number 1 and layer number 2, that is dy. Now let us consider at time t is equal to 0. Let us consider at time t is equal to 0, fluid particle A, this is the fluid particle A, and in this layer this is the fluid particle B. This is the fluid particle B. Right, see here, in this layer, right, this layer is moving with velocity. Let us consider this layer is moving with velocity u and this layer is moving with a velocity u plus du. Definitely this layer having more velocity, na? Definitely this layer having more velocity as compared to this velocity, right? So let us consider this layer having velocity u plus du and this layer having velocity that is equal to u, right? So this is the layer number 1. Layer number 1 is moving with velocity u and layer number 2 is moving with velocity u plus du. At a particular time, in this layer, in the layer number 1, let us consider fluid particle A, and at the same time I am considering another fluid particle B in the layer number 2, right? Now if you join point A and point B, or if you join particle A and particle B, so this is nothing but the timeline, na? This is nothing but the timeline. This is the timeline. This is the timeline. This is the timeline at time t. At time t. Let us consider. Right. This is the timeline at time t. Now, if I am talking about the time interval dt, right? If I am talking about the time interval dt, or if I am talking about t plus dt time, right? This is the timeline corresponding to the time t. Now if I am talking about the at time t plus dt, so definitely this fluid particle reaches to here, this fluid particle reaches here, and since this fluid particle having more velocity, this fluid particle cover more distance. So let us consider this fluid particle reaches to here, okay, right? Or I can say this is the A dash and this is the B dash. Right, now again you can easily draw the timeline at time t plus dt. So this is the timeline at time t plus dt. This is the timeline. This is the timeline. This is the timeline at time. This is the timeline at time t plus dt. So in dt time interval, the A particle covers, let us x1 distance, and B particle covers, let us consider x2 distance, right? Why particle number B covers more distance? Because this layer, that layer number 2 having more velocity as compared to the layer number 1. That's why layer number B, that's why the particle number B covers more distance as compared to the particle number A. Right? So x1 is the distance traveled by the particle A in dt time interval, and x2 is the distance traveled by the particle B in dt time interval. Fine. Now see here. Now see. So see. Now let us consider this is the angular deformation, that is a d phi. Let us consider this is the angular deformation which is d phi, right? And what about this distance? What about this distance? What about this distance? So simply we can say this is nothing but the x2 minus x1. This distance we can simply say x2 minus x1, right? So we can write from the geometry that tan d phi is equal to, this is x2 minus x1 upon dy, right? Tan d phi, tan theta is equal to, we can write na x2 minus x1 upon x2 minus x1, that is a perpendicular divided by base. So x2 minus x1 divided by dy. And what is the x2? What is the x2? That x2 is nothing but the distance traveled by the particle B in dt time interval. So we can write that x2 is equal to, this is u plus du into dt na. That x2 is nothing but the u plus du into dt. And what is the x1? That x1 is equal to u multiplied by dt, right? That distance, distance is equal to velocity multiplied by time, na? Velocity is equal to distance per unit time. So distance is equal to velocity multiplied by time. So x2 is u plus du into dt and x1 is u into dt, right? And this d phi is very, very small. This d phi is very, very small. Therefore, tan d phi is approximately equal to d phi. Tan d phi is approximately equal to d phi. Is it clear? So we can write d phi is equal to x2, this is u plus du into dt minus x1 u into dt upon dy. So simply we can write that d phi is equal to, this is du into dt upon dy, and from here we can write that d phi by dt is equal to du by dy. And this is the equation number, let us consider this is the equation number 2, right? This is the equation number 1 and this is the equation number 2. The d phi by dt is equal to du by dy. And what is the du by dy? The du by dy is nothing but the velocity gradient in the y direction, right? What is the du by dy? What is the du by dy? The du by dy is velocity gradient in y direction, right? So from equation 1 and equation 2, from equation 1 and equation 2, can we write that tau is equal to mu du by dy, right? Can we write from equation 1 and equation 2 that tau is equal to mu du by dy, right? Or in general or in general, we can write the shear stress experienced by any layer which is present at a y distance from the bottom plate, the tau at any y is equal to mu du by dy at that y, mu du by dy at that y. So we can write in this way also, right? So this is also a mathematical expression of Newton's law of viscosity. This is also a mathematical expression of the Newton's law of viscosity. But this mathematical expression is more useful as compared to the equation number 1, right? This mathematical expression is more useful, right? And you must remember this expression. Because this is a very, very important expression. This is the mathematical expression of Newton's law of viscosity. Is it clear to everyone? Now beta, this equation is applicable. This equation is applicable for laminar flow. This equation is applicable for the laminar flow, right? If above the plate, if flow is laminar, then you use this mathematical expression. If flow is turbulent, it is, right, this formula is not applicable. If flow is turbulent, then this formula is not applicable. This formula is applicable only when the flow is laminar, when the fluid flow is laminar, right? The second important point, fluid must be Newtonian fluid. Fluid must be Newtonian fluid. And third important point, u is function of y only. Right? Then you can use this Newton's law of viscosity mathematical expression. Flow must be laminar flow, fluid must be Newtonian fluid, and u is equal to, or u must be function of y. Right? Now what is the Newtonian fluid? It is simple now. What is a Newtonian fluid? 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 So it is simple. A fluid which obeys the Newton's law of viscosity. A fluid which follows the, right, a fluid which follows the, a fluid which follows the Newton's law of viscosity, a fluid which follows the Newton's law of viscosity, a fluid which follows the Newton's law of viscosity, a fluid which follows the Newton's law of viscosity is known as Newtonian fluid. So can you tell me some examples of Newtonian fluid? Right? Can you tell me some examples of Newtonian fluid? Examples: air, water, kerosene, benzene, petrol, glycerine, etc. Right? These are some example of the Newtonian fluids. So it is simple. Newtonian fluid is a fluid which obeys the Newton's law of viscosity, or which follows the Newton's law of viscosity. Right? There are non-Newtonian fluids also. Right? There are non-Newtonian fluids also. So we will discuss non-Newtonian fluids later on. So whatever we discuss, whatever whatever we discussed here, that is related with the Newtonian fluid, right? Whatever we discuss here, that is related with the Newtonian fluid. For the non-Newtonian fluid, we will discuss later on. Okay, so is it clear to everyone? Till this point, it is clear to everyone? Till this point, it is clear to everyone? Any doubt? Yes, mercury also. Yes, mercury also. Right, mercury also. Yes. Okay. Now see here. If I draw a graph between shear stress and shear strain rate, right? If I'm talking about the graph between shear stress and the shear strain rate, shear stress and the shear strain rate, right? So in a y-axis, there is a shear stress, that is tau. In y-axis, there is a shear stress, that is tau. In a x-axis, there is a shear strain rate, shear strain rate or angular deformation rate, or angular deformation rate, that is d phi by dt, right? So if I want to draw the graph for the Newtonian fluid, so are you able to draw the graph for the Newtonian fluid? Are you able to draw a plot for the Newtonian fluid? In this graph, shear stress versus shear strain rate graph, are you able to draw the graph for the Newtonian fluid? Yes, we can draw, na? Definitely we can draw. This equation is like y is equal to mx, na? Right? This equation is y is equal to mx, na? See, tau is equal to mu du by dy. Tau is equal to mu du by dy. Right? This is your y-axis. This is your x-axis. Right? So tau y is equal to, this is mu multiplied by this, this is y. Sorry, x. I'm sorry. Right? Or we can say this equation is similar to y is equal to, this equation is similar to y is equal to mx. Y is equal to mx. Right? Y is equal to mx. So y is equal to mx. This is a straight line equation having slope m. Right? Y is equal to mx is nothing but this is the equation of a straight line having slope m. So this equation is similar to this equation, na? Is it okay? So for the Newtonian fluid, this is the graph. For the Newtonian fluid, this is the graph. This is for Newtonian. This is for Newtonian fluid. Right? And what about this angle? What about this slope? What about this slope? What about the slope? Can we say this slope represent the absolute viscosity of the fluid? Can we say this slope represent the slope of tau versus du by dy plot, right? Slope of tau versus du by dy plot, or for Newtonian fluid, right? For Newtonian fluid, slope of tau versus du by dy plot represent the viscosity, right? The slope, right? That slope, this slope represent the viscosity. Okay, so if I'm talking about the, see, if I'm talking about the two graphs, let us consider, again I am considering the tau versus du by dy plot. Again I am considering tau versus du by dy plot, or tau versus d phi by dt. Same thing, na? D phi by dt is equal to du by dy only. Now I'm showing two graphs, graph number 1 and this is the graph number 2, right? This is the graph number 1 and this is the graph number 2. Can you tell me which graph is for liquid and which graph is for the gases? Or simple, can you say which graph is for the water and which graph is for the water and which graph is for the air? Right, water and air both are Newtonian fluid. So if I ask you one simple question, which graph represent air and which graph represent the water? Okay, now I'm giving, okay, take a hint. For water, viscosity is 1.002 into 10 to the power minus 3 Pascal second at 20 degrees Celsius. Na? Viscosity is strongly dependent on the temperature. So at 20 degrees Celsius, the viscosity of the water is 1.002 into 10 to the power minus 3 Pascal second. And if I'm talking about the viscosity of air, so this is 0.0184 into 10 to the power minus 3 Pascal second at 20 degrees Celsius. Right? So obviously, it is very much clear that water viscosity is more, na? Water viscosity is more as compared to air, na? Water viscosity is more as compared to the air, na? Yes or no? So graph having more slope, the graph having more slope represent the water and the graph having less slope represent the air. Graph having more slope represent the water and the graph having less slope represent the air. That means graph number 2 is for water and graph number 1 represent the air. Right? And in general, liquid shows higher viscosity as compared to gases. Right? Liquids shows higher viscosity as compared to the gases. Is it clear? Is it clear to everyone? Now come to the units. Now come to the units. Is it clear or not? Now come to the units. SI unit. What is the SI unit? What is the SI unit of viscosity? SI unit. What is the SI unit? Okay, so tau is equal to, see here, tau is equal to mu du by dy. So we can say mu is equal to tau by du by dy, right? Mu is equal to tau du by dy. Now see here, now see that SI unit, if I am talking about the SI unit, now SI unit tau, what is the unit of tau? That is Pascal, right? And what is the unit of du by dy? What is the unit of du by dy? The du by dy unit is per second, na? U, meter per second divided by meter. So meter is cancelled out, and this is 1 by second. 1 by second. So simply we can say that SI unit is Pascal second. SI unit is Pascal second. Or 1 Pascal is equal to, we also know 1 Pascal is equal to 1 Newton per meter square. 1 Pascal is equal to 1 Newton per meter square. So we can say this is also equal to Newton second meter square, right? So SI unit for the viscosity is, SI unit for the viscosity is Pascal second or Newton second per meter square. Now come to the MKS unit. Come to the MKS unit. What about the MKS unit? What about the MKS unit? So see, MKS unit is Newton. We can write Newton as kg meter per second square, right? Kg meter per second square into second divided by meter square. So second cancel out, meter cancel out, and this is equal to kg per meter second, right? This is the MKS unit, kg per meter second, right? And also we can say that 1 Newton second per meter square is equal to 1 kg per meter second, 1 kg per meter second, right? This is very important relation. In some question, that unit of viscosity is given in MKS unit, right? In some question, that unit of mu, unit of viscosity is given in MKS system. So you must remember that 1 Newton second per meter square is equal to 1 kg per meter second. Okay, now come to the CGS unit. Come to the CGS unit. Now CGS unit, see, CGS unit. Now CGS unit, can we write dyne second per centimeter square, right? The CGS unit is dyne second per centimeter square, and this dyne second per centimeter square, this dyne second per centimeter square is called poise, right? Dyne second per centimeter square is called poise. So 1 poise is equal to 1 dyne second per centimeter square, right? This is also equal to, since 1 Newton second per meter square is equal to 1 kg per meter second, therefore 1 dyne second per centimeter square is also equal to 1 gram per centimeter second, 1 gram per centimeter second, right? So 1 poise is equal to 1 dyne second per centimeter square, and this is also equal to 1 gram per centimeter second. So this is the CGS unit. Now can you establish the relation between the SI unit and the CGS unit? Can you establish the relation between the SI unit and the CGS unit? Relation between SI unit and CGS unit. Relation between SI unit and the CGS unit. Can you establish the relation between SI unit and the CGS unit? So see that 1 poise is equal to 1 dyne second per centimeter square na? And we also know that 1 dyne is equal to, or 1 Newton is equal to 10 to the power 5 dyne, or 1 dyne is equal to 10 to the power minus 5 Newton. Right, so 1 dyne is equal to 10 to the power minus 5 Newton, 10 to the power minus 5 Newton second. Now centimeter square, so this is 10 to the power minus 4 meter square. Right, so 10 to the power minus 4, so this comes 10 to the power minus 1, that means 0.1 Newton second per meter square. So 1 poise is equal to 0.1 Newton second per meter square, or 0.1 kg per meter second. So this is very, very important relation. Right, you must remember this relation. Right, this is very, very important relation, that 1 poise is equal to 0.1 Newton second per meter square, or 0.1 kg per meter second. Fine. Okay, so can you write viscosity in terms of fundamental dimensions? Can you write viscosity in terms of fundamental dimensions? Can you write viscosity in terms of fundamental dimension? Can you write viscosity in terms of fundamental dimension? Yes, we can write. Yes, we can write. Right, yes, we can write. So see here, in terms of fundamental dimensions, right? So simply we can write, we know that, right, kg per meter second is the unit of the viscosity. So in terms of fundamental dimensions, that is m L minus 1 or m L minus 1 T minus 1. Right, so viscosity in terms of fundamental dimension. So simply that is m L minus 1 T minus 1, that is kg per meter second for kg m, meter L T. So m L minus 1 T minus 1. So this is the viscosity in terms of fundamental dimension. Is it okay? Okay. Now this is your homework problem. Right, this is your homework problem. Try this question and let me know the answer in Telegram channel. So this is a one MCQ question. Right, this is the MCQ question, this is the homework for you, and this is the another question. Right, this is the another question, this is the MSQ question. Right, this is the question number 2, this is also your homework question. Right, so first you will try yourself, right, and if you are not able to solve the problem, then definitely I will tell you. Right, so try yourself first, right, and tell me the answer in the Telegram group. Right, I'm in Telegram group, that English Gate Wallah English channel, right, that Telegram group. So try to answer these questions. Right, this is a question number 1, this is the MCQ problem, and this is the MSQ problem. Okay, so whatever we discuss in today's class, right, we discuss about the specific gravity, we discuss about the relative density, right, we discuss about viscosity concept, we discuss about Newton's law of viscosity, right. So whatever we discuss in today's class, that is clear to everyone. Beta, whatever we discuss in today's class, that is clear to everyone. Whatever we discuss in today's class, that is clear to everyone. So tomorrow's class, right, tomorrow class we will discuss about number of cases related with the Newton's law of viscosity. The Newton's law of viscosity is one of the important topic in a fluid mechanics. Number of times you are getting a question from the Newton's law of viscosity, and beautifully framed question, right? So try this question first, then in tomorrow's class we will discuss number of cases related with the Newton's law of viscosity. Okay, so thank you so much guys, and bye bye, take care, and good night everyone. Good night.